Okay, YouTube, in this video we're going to continue solving polynomial equations of higher degree, and we see that we have this fourth degree equation here. In our last video we looked at a couple of third degree equations and learned that we got 3 solutions for each. So maybe a conjecture here would be that we get 4 solutions for this. A couple of properties I want to look at about the roots of polynomial equations kind of highlight that first statement that we just kind of explored. But basically it says if a polynomial equation is of degree n, so we have an nth degree equation, it says then counting multiple roots, we're going to write this here, repeated roots. Then counting repeated roots, which I mean like this, like you could get, say, like 2 as an answer, like 3 times in a row. You would count those separately. But basically, counting multiple roots separately, an nth degree equation has n roots. So basically, the implication here is that nth degree implies n roots, or solutions, or zeros or x-intercepts, basically, okay? So it says also here another property, a plus bi is a root of a polynomial equation with real coefficients such that b does not equal 0. That means that there's actually an imaginary part to this, b doesn't equal 0. Then the imaginary number a minus bi is also a root. So we say imaginary roots, if they exist, occur in conjugate pairs. So essentially, if a plus bi is we're going to write a solution here, then a minus bi must also be a solution. And that's the important bit of information off of that. I would say that solutions, if they ever exist as imaginaries, have to occur in conjugate pairs. Okay, so let's take a look at this polynomial right here. If we were asked to go solve this right here, I notice it's a fourth degree. I can't, factor it, but it is set equal to 0 for me. Let's find the factors of the constant term and the factors of leading coefficient and get our list of possible rational roots going here. So we say plus or minus. Factors of 13 are just 1 and itself. It's a prime number. And we say factors of 1 are just 1. So we'd say, writing this in roster notation, we'd say the only possible rational zeros that would work here are plus or minus 1 or plus or minus 13. So let's go ahead and start by just guessing and checking here. I'm going to drop in my coefficients. So 1x to the fourth, negative 6 of these x to the cube things, 22 of these x to the second things, negative 30 of these x to the first things, and then 13 constants. So we say 1. Okay, we'll start with 1. So 1 times 1 is 1. 1 here. We say negative 5 when we add those together, negative 5 when multiplying these, and then this leaves 17. 1 times 17 is 17. Add these together, we get a negative 13. Kind of nice because I have a positive 13 right there. This leaves a 0 remainder. So a couple things we want to write here. We said solve this. So what are we looking for? Well, we're looking for the zeros. So I'm going to list these over here. I anticipate that I'm going to get 4 of them. But my first 0 is x equals 1. That is to say that x equals 1. When I plug that into the function, remember we get a y value of 0. So it's an x-intercept. But it's also to say that the factor that is associated with this is x minus 1. And so if x minus 1 is one of the factors of this, then we'd say that this is the other factor now. In the last video, I wrote this as x minus 1 times this, and this is going to be x cubed minus 5x squared plus 17x minus 13, plus, of course, a remainder of 0. But basically, I wrote this as x minus 1 times all of this gets me back to the original. But what I want you to see is this thing right here, I don't need to write it as this times this any longer because I already took care of this when I listed that x equals 1 as one of the zeros. Okay, get it? So what I want you to see is that we could just keep working with this right here. And this, if I were to set it equal to 0 and go solve for its zeros, well, I suspect that there would be 3. It's a third degree thing. But I also see that I can't factor this by grouping. Grouping is just not going to work here. So what we're going to do is we're going to keep running with this sucker. And so I'll tell you, let me see if I can get this bottom stuff out of the way. Be hopeful that I can here. Ooh, this is really exciting because what we can do now is we can just build off of this. And I've had teachers that show me this before and other people that I work with that do it. I don't do it often, but you can build off of this. And we could say, let's just keep going. Now, because 1 worked, here's the interesting thing about it. We're going to put another number out here and say, let's synthetically divide this polynomial. But 1 could work again. And so I want to check 1 just to see if it does or doesn't work. So we say 1 times 1 is 1. 1 plus negative 5 is negative 4. 1 times negative 4 is negative 4, of course. And looking at this is really kind of an interesting thing. We notice we get 0 again. So what this means is I'm going to go up here and add 1 to the list. It also means that the factor x minus 1 was a factor of this polynomial twice. And now we could even write this as x minus 1 times x minus 1 times this quotient polynomial that you see right here. But what I want you to see is we could either build off of this again and do synthetic division again, or what we could do is at this point, and I'm going to recommend this, because it's quadratic, let's just go ahead and put our variables back onto this and let these be the coefficients, and we'll try to solve this by factoring. So in terms of factoring, I don't notice any numbers other than 1 and 13 as factors of 13, and those certainly are never going to sum to a negative 4. So no factors of positive 13 sum to negative 4. So what we're going to do here is we're going to find our other two zeros using the quadratic formula. So we have, let's list these here. We have A, B, C are 1, negative 4, 13 respectively. I'll put a little box around this little codex of values over here, and we say, okay, so we have x equals negative b, so negative negative 4, plus or minus the square root of, we have negative 4 squared minus 4 times our a value is 1 times our c value is 13, and this is all over 2 times a, where a is 1. So let's simplify this here. Don't know if I'm going to get real or imaginary results yet till we do our square root, but I do see this is a 4 over 2 here for our negative b over 2a part. So we say 16 there, and this would be 4 times 13, so 4 times 10, let's see, is 40. 4 times 3 is 12. 40 plus 12 is 52, so we have minus 52. This isn't good, at least in terms of getting real results. We're going to get imaginary results, which is fine. I just want to bust out my calculator here because I don't want to make a mental error on something like this. We say 16 minus 52. So we have this negative 36 here. So we have x equals 4 plus or minus the square root of negative 36. Fortunately for us, we did get a perfect square under our radical. Unfortunately for us, I don't know why I look at imaginaries as being negative things. I just don't like them as much as reals, I guess. But we get this. Remember, put your eye out front. So what we end up with, and I apologize for my rerouting of my order here, but we'd get 4 plus or minus 6i all over 2. And that's important because we could reduce all of this. Everybody has a factor of 2 in common. So we're going to say 2 plus or minus 3i all over 1. So our other two zeros, we're going to list these up here, 2 plus or minus 3i. And so in terms of these, go ahead and put a box around this, these properties that you see up here, one that I wanted to highlight is this. If it's nth degree, which it was 4th degree, then we have n roots. So we have 4 solutions. We're going to write 4 solutions here because it's 4th degree. And also this, if we have a plus bi, which was this 2 plus 3i, you can see that because we would have like a quadratic sense where we had negatives inside of a square root, we're always going to have an irrational number that is imaginary, so we're going to get complex conjugates. Okay, cheers.